We introduced deep points, a new representation and consolidation method for 3D point sets. The key idea is to augment each surface point into a deep point by associating it with an inner point. The inner point resides on a mesoskeleton, which consists of a mixture of 1D skeletal curves and 2D surface sheets. The strength of this new representation stems from the fact that it is comprised of both local and non-local geometric information, which we demonstrate to be powerful in point cloud consolidation and shape completion. Given a real model, the input to our algorithm is an unorganized and unoriented raw scan point cloud with significant missing data. We start by performing an initial consolidation using the WLOP technique to obtain a denoised, oriented, and down-sampled point set. We then copy and sync these sample points down into the shape interior to construct a set of anchor points. We further consolidate the anchor points to form the mesoskeleton using anisotropic neighborhoods. Finally, the mesoskeleton provides the non-local information that guides surface point consolidation, and it allows us to complete large missing areas. The output of our algorithm is a D-points representation, which consists of a mesoskeleton with proper topology, a complete and consolidated point set surface, and a one-to-one mapping between the two. This example demonstrates our optimization objective, which is to fairly distribute the deep points across the surface and mesoskeleton, such that the deep point orientations agree with the surface normals. The optimization converges where the inner points form a coherent mesoskeleton, and the surface points are consolidated and missing regions are completed. Real scan data often contains large missing areas. In this chair model, our mesoskeleton is able to guide the surface completion of both interior holes and open boundaries. There are two key parameters in our approach: the surface neighborhood size, sigma p, and the point settling threshold, omega. These two examples show that larger surface neighborhood values, sigma p, often lead to representations that are more robust against input noise and large missing parts. On the other hand, the consolidated surface may not represent the surface details as well. The parameter omega controls how deep the inner points can sink into the volume of the shape. Since the inner points settle sooner under smaller values for omega, the mesoskeleton follows the surface details more closely, but is also more sensitive to noise. With larger omega, the inner points may not meet the opposing front due to missing data, so the final skeleton may deviate from the proper medial position. This may cause the final consolidated shape to have a bigger volume. Here's another set of results using different omega values. D points allow us to easily include different shape priors. Here, the default prior preserves local volume in the completed region. As an alternative, we also provide a prior that minimizes the volume of the missing area. To preserve high-frequency details, we apply an additional post-processing to reintroduce sharp features and small geometry details from the input. Here, an edge-aware point resampling technique is employed to upsample the surface points first, and then project the new samples near the input to the underlying surface using bilateral projection. D points outperform the basis surface reconstruction approach in terms of both topology preservation and robustness to noise and outliers. Using the consolidated D points, the thin and adjacent structures are better preserved. In this example, our algorithm outperforms the state-of-the-art skeleton extraction methods such as ROSA and L1 medial skeleton. The Poisson reconstruction of the surface based on our deep points is naturally smooth and complete. Unlike the existing approaches, which produce skeletal curves regardless of surface topology, the D-points mesoskeletons can better respect the topology of non-tubular shapes. Quantitatively, evaluations show that the models reconstructed using D-points are noticeably more accurate than the ones reconstructed from input points directly. As you can see from this live demo, the completion of the surface by our technique is intuitive since it follows a coherent mesoskeleton. Our completion respects the shape context by extrapolating the existing surface guided by the mesoskeletons, rather than completing the surface with context-oblivious data. Thank you for watching our video about deep points.